Hello, YouTube. We are live.
Hello, everyone. Welcome back to the MLSys seminar. Today, we're super excited to have Deepak Narayanan, and he actually graduated with his PhD in computer science in 2021 from Stanford, where he was advised by Matei Zaharia. Deepak is a senior applied research scientist at the ADLR group at NVIDIA, where he builds software systems to more efficiently train and serve LLMs. During his PhD, he completed a ton of exciting work on pipeline parallelism and cluster scheduling. And yeah, he's currently working on the Megatron LM team. So with that, Deepak, I'll let you take it away with your talk, and then we'll loop back towards the end with some questions and discussion.
Awesome. Yeah, thanks a lot, Simran, for the introduction. So yeah, I'm excited to be here today to talk about some work we've been doing at the NVIDIA Megatron LM team on training large language models at scale. So machine learning has powered state-of-the-art results across a broad range of applications. And as the amount of compute and training data has increased, so too has the size of these models. So this is a bit of a dated graph, but it shows the sizes of various state-of-the-art models used in natural language processing. And we can see that over the last 5 or so years, the number of parameters in these models have increased by almost 4 orders of magnitude, drastically increasing the number of compute operations needed to train these models as well. Training modern scale models with hundreds of billions or even a trillion parameters is challenging for a couple of different reasons. First, the parameters of these models alone do not often fit in the main memory of the largest accelerators that we have currently available, such as A100 or H100 GPUs. And this does not even include the other intermediate data that we also need to keep in memory for training. Training these models also requires a large number of compute operations. This means that even if we were able to offload parameters and other intermediate data to the CPU from the accelerator, training would still be really infeasible on a single GPU. We estimate that training a 175 billion parameter GPT-3 model for about 300 billion tokens would take about 288 years on a single NVIDIA V100 GPU. And newer models are much more computationally expensive. And finally, we can group inputs into large batches in order to amortize things like communication overheads. But this can require more tokens to achieve the same loss. And this limits the scalability of techniques like data parallelism, which shard a batch of data over many workers or devices. So in HPC terms, we need to concentrate on strong scaling, that is trying to parallelize a given problem over as many GPUs as possible, as opposed to increasing the problem size as the number of accelerators increase. So in this talk, I'm going to try to motivate the need to think carefully about how different parallelism dimensions interact with each other, in order to train really large models efficiently at scale. I'll also briefly touch on some lower level optimizations that we needed to do on both the computation and communication sides in order to sustain efficient training. So the rest of this talk is organized as follows. First, I'm going to briefly discuss existing methods of parallel model training. Then I'll discuss how these different methods of parallelism can interact with each other, given their various trade-offs. And then I'm going to comment on a few domain-specific optimizations that greatly improve training performance at scale. And then I'm going to talk about some recent advancements that have changed the paradigm of under which we operate in this distributed training regime, and also talk about some open questions. So let's get started. So there are a couple of different ways we typically try to distribute model training over multiple accelerators. At a high level, when training a model, we have a forward pass and a backward pass. The forward pass involves taking some inputs, passing them through the model and generating some predictions that could be incorrect. And then in the backward pass, we essentially propagate fixes to the model based on some target labels. Typically, we do this in iterations, and each iteration of training will average gradients over multiple inputs called a batch. The most common form of parallelism is called data parallelism, where we take a given batch of inputs and split it over multiple devices. Each device has a copy of the model, and then at the end of every iteration, we aggregate updates from each of these copies of the model. And these updates are aggregated usually using a communication primitive such as allReduce. Instead of replicating the model across multiple devices and splitting the data, we can also split the model parameters of the model itself across multiple devices. And this is called model parallelism. There are a couple of different ways of splitting the model's parameters across these devices, and this leads to various trade-offs. So with data parallelism, we're replicating the model. At least we're replicating the model and splitting the data. And at the end of every iteration, we need to perform an all reduction of the weight gradients to make sure that every device has the same copy of the weights post the training iteration. The vanilla version of data parallelism cannot be used in isolation for large models since the model is copied, but it can be used on smaller model shards. With tensor model parallelism, we're going to split each layer or operator of the model over multiple devices. So this is a particular splitting strategy used in Megatron for transformer-based models. Transformer models are essentially a collection of matrix multiplications. And so when we're using tensor parallelism, we're essentially distributing these matrix multiplications over multiple GPUs. The particular splitting strategy that we use here involves splitting this weight matrix A column-wise and this weight matrix B row-wise. And this helps to reduce the total number of synchronization points that we have. In particular, we need to So in this particular diagram, G is an all reduction in the forward pass and the identity operation in the backward pass. And F is the conjugate of that. This all reduction can be somewhat expensive when performed across multi-GPU servers. And so generally, we try to use tensor model parallelism only within a single multi-GPU node. And then finally, with pipeline parallelism, we split the layers or operators in the model over multiple devices. And then we also will split each batch of inputs into smaller micro batches and then parallelize execution across these micro batches. To be very concrete, let's look at this visually. So this is a model that we're splitting over 4 devices. So let's say that if the model has 8 transformer layers, what we're going to do is we're going to assign the first 2 transformer layers to the first device, the next 2 to the second device, and so on. Now, in order to perform a single forward and backward pass through the model, we're going to need to take a single input, pass it through device 1. Device 1 performs its computation, represented by this blue box, computes and what we call an output activation, and then this output activation needs to be communicated to the next device, and the second device can't start its computation until it's received this activation from the first device. And so what that means is that there is this sequential data dependency across each of these devices. And lots of these devices are idle. In particular, at any point in time, only one device is active. So very quickly, you can see that this scheme has pretty poor utilization and low throughput. So instead, what we can do is we can take this input batch A and split it into smaller micro batches. Let's say that this input batch A has 4 inputs in it. What we can do is we can split that input batch of 4 into 4 micro batches of size 1, and then pipeline execution across those micro batches. In particular, this is what this looks like. We note now that we only have sequential data dependencies between devices for a given microbatch. In other words, device 2 now only needs to wait on device 1 for this output activation of microbatch A1 before it starts computation. So no longer do you have to wait for for device 1 to complete computation for all 4 input samples in this batch. Instead, we can immediately start processing on device 2 as soon as just a single input's worth of computation is completed on device 1. After we complete computation for all of these forward and backward passes for these 4 micro batches, then we can step the optimizer, which is basically around here, and then we can update the weights and move on to the next training iteration. It's easy to see from these figures that this is much more efficient compared to the naive case where we only have a single batch. But there are still some idle periods. We haven't completely eliminated these idle periods from these timelines. We call the periods of time that each device is idle at the start and end of a training iteration, the pipeline flush. And these are basically fundamental, right? Basically, the pipeline flush is the time that devices need to wait for inputs to actually flow through the pipeline and then subsequently get drained out. So to summarize, with pipeline model parallelism, we need to perform point-to-point communication between consecutive pipeline stages. And we have these pipeline bubbles at the start and end of every batch. We can actually exactly quantify how much time is spent in the pipeline bubble. It's actually going to be equal to P-1 microbatches worth of forward and backward passes, where P is the number of pipeline stages. So in the previous figure, the number of pipeline stages was 4, and the size of the pipeline bubble was 3 microbatches worth of forward and backward pass. Okay, so now that we have looked at each of these parallelism modes in isolation, we can talk through what happens when we try to compose them. So one thing to note here is that each of these parallelism dimensions do not perform well in isolation at large scale for various reasons. For example, with both data and tensor parallelism, we need to perform all reductions. And if we try to scale out to a large number of GPUs, the amount of communication that we need to perform across those GPUs can quickly become overwhelming. This is more true for tensor parallelism than data parallelism, since the tensor parallelism communication that we need to perform is actually going to be per microbatch. For data parallelism, we need to only communicate once at the end of every training iteration. And so we can actually perform data parallelism at very high GPU counts. tensor parallelism becomes very unwieldy cross-node. So usually within a node, we have multiple GPUs, usually 8, and those 8 GPUs are connected by very high bandwidth links called NVLink. And so communication within a server is actually quite fast. But communication across servers, even with latest technologies like InfiniBand, is much slower. And so we really can't perform tensor parallelism communication across nodes without significantly impacting training throughput. It also turns out that we can't naively combine parallelism dimensions. If we try to do this in a haphazard fashion, we're also going to get low training throughput. And I'll expand on this point a little bit more in the next couple of slides. And so actually using these 3 dimensions in some sort of unified way requires us to reason carefully through the interactions between these different parallelism modes. So very concretely, I'm going to consider now the trade-off between tensor and pipeline model parallelism. So I'm going to assume that the total number of GPUs that I have at my disposal is n. I'm also going to assume that the tensor model parallel size is t, and the pipeline model parallel size is p. So I'm only going to use tensor model parallelism and pipeline model parallelism in this particular example. So I have this simple equation that t times p is going to be equal to the total number of GPUs that I have, which is n. Now I can remember that I said that I can exactly quantify the size of the pipeline bubble. The total time spent idle on each of those devices is going to be p minus 1 microbatches of forward and backward compute. I'm going to assume that the amount of compute in a forward pass for a given microbatch is going to be t sub f, and the amount of compute or the runtime of the backward pass for a given microbatch is going to be t sub b. And so the total time spent in the pipeline bubble is going to be p minus 1 times tf plus tb. And I can now compute the fraction of essentially, I can also compute the ideal amount of time that should be spent doing computation for m microbatches, right? That's just going to be m times tf plus tb. And so the pipeline bubble size, which is the fraction of the ideal time that you spend in your computation, is just going to be the ratio of those two quantities. TF plus TB cancel out in both the numerator and the denominator. And so this simplifies out to P minus 1 divided by M. Now I can leverage the fact that T times P is equal to N to essentially compute this expression for the pipeline bubble size in terms of the number of GPUs, which is a constant, the tensor model parallelism size, and the number of microbatches. Very quickly, we can see from this expression that as the tensor model parallel size increases, as T increases, the pipeline bubble size actually decreases. So what this suggests is that if we're just using tensor model parallelism and pipeline model parallelism, I actually maybe want to use as large tensor model parallel size as possible. This actually is not quite true because there's this other effect that I haven't talked about yet, which is the all-reduced communication associated with tensor model parallelism, right? And so as T increases beyond the number of GPUs in a server, we're going to have to do those all-reduced communications cross-server, and this is going to be pretty expensive. So I can show these two effects empirically. So here I'm going to show results for 162 billion parameter GPT model on 64 80GB A100 GPUs. So on the y-axis, I'm going to show the achieved throughput in terms of teraflops per second. So tera floating point operations per second per GPU. So I could have equivalently shown the total aggregate throughput but all I'm doing here is I'm taking that total aggregate throughput number and dividing by 64 because I'm using 64 GPUs across all of these different configurations. And then on the x-axis, I'm going to show different training configurations. In particular, I'm going to show different combinations of pipeline parallelism size and tensor parallel size. Note that I have this constraint that the total number of GPUs is 64. So all of these configurations are going to respect the constraint that T times P is going to equal 64. And so one thing I want to note here is since I'm showing throughput, a higher number is better. We want to achieve the highest aggregate throughput as possible. And so what we actually see is as I increase the pipeline parallel size initially, throughput increases, and then it peaks at pipeline parallel size of 8 and tensor parallel size of 8. And then it starts decreasing again. And so now you might think, what's so special about this central point? It turns out that this number of 8 is actually really important in this particular setup. When the tensor parallel size is less than or equal to 8, we're able to perform the all reductions within a server using those high bandwidth NVLink interconnects that I told you about earlier. Whereas once we increase the tensor, sorry, I misspoke. So in the left part of this graph, the tensor model parallelism all reductions are actually performed across servers. This is actually really expensive, which is why throughput is low on the left side of this graph. And then on the right side of this graph, when the pipeline parallel size is really large, the pipeline bubble is actually also large. So remember that the pipeline bubble size is proportional to P. And so as the pipeline bubble size increases, the amount of time these resources spend idle also increases, and that also decreases throughput. And so we essentially see that there's this happy middle ground of 8,8 where the pipeline bubble size is not super large, and also we're able to perform these expensive all reduced communications for tensor parallelism within a multi-GPU node. It turns out that the configuration space when you're training models at scale is actually quite large. So we briefly touched on the impact of pipeline and tensor parallelism on each other, but it turns out that the degrees of a pipeline and tensor parallelism also interact with data parallelism, and so we need to kind of reason through how all three of those dimensions interact with each other. It also turns out that things like the pipelining schedule also affect the trade-offs that we see. So this is the standard schedule that I showed earlier, where essentially if we have a transformer model with 8 layers, we assign contiguous layer chunks to each of these devices. So if the model has 8 layers, device 1 is going to get the first 2 layers, device 2 is going to get the next 2 layers, device 3 is going to get the next 2 layers, and so on. But what we can actually do is we can assign transformer layers to stages in a sort of interleaved way and then wrap back around. So what that means concretely is that device 1, now instead of having layers 1 and 2 in the model, will have layers 1 and 5. Device 2 will have layers 2 and 6. Device 3 layers 3 and 7, and device 4 has layers 4 and 8. And so essentially now each device has to perform 2 phases of forward passes, right? So first it performs the forward pass for micro batch 1 and transformer layer 1. It completes that computation, passes on a tensor to device 2 so that it can do the computation for layer 2. And then finally, once we get to device 4, and device 4 completes the computation for layer 4, then it passes a tensor back to device 1, which will now then do the computation for microbatch 1 and transformer layer 5. The advantage of having this interleave schedule is that we're now reducing the latency needed for device 4 to actually receive inputs, right? And so the pipeline bubble size now is in effect halved, right? It doesn't need to wait for P-1 microbatches worth of 2 layers of computation. Instead, you just need to wait for P-1 microbatches of 1 layer of computation. And so this decreases the pipeline bubble size. And in these simplified diagrams where I'm assuming that communication is free, you can quickly see that the time needed to complete all the computation for a single iteration decreases, right? Simply because the pipeline bubble size is now smaller. But it turns out that this smaller pipeline bubble doesn't come for free. It actually increases the amount of communication as well. This is a byproduct of us having to go through the same set of devices multiple times, right? So now, instead of just going from device 1 to 2 to 3 to 4 and completing the forward pass, we need to again go through devices 1, 2, 3, and 4, right? And so that effectively you're doubling the amount of point-to-point communication that you need to perform, but you're halving the pipeline bubble size. So we can see how each of how these two effects actually influence end-to-end training speed. So this is going to be results for a 175 GPT model on 96 A100 GPUs. As before, I'm going to show per GPU throughput on the y-axis, and a higher number is better. And I'm going to show actually the batch size on the x-axis. And so the interesting thing about the batch size parameter is that as we increase the batch size, the amount of communication that we need to perform is also proportionally increasing. And so what we see is that in the small batch size regime, the interleave schedule is much faster than the non-interleave schedule. Note also when the batch size is really small, the pipeline bubble size is large. Remember, the pipeline bubble size was P-1 divided by M. That M factor in the denominator is influenced by the batch size. And so for a larger batch size, that pipeline bubble size becomes smaller. But we can quickly see that the gap between the two decreases as the batch size becomes larger, partially because in the non-interleave schedule, the pipeline bubble is smaller to begin with, right? And so the lift you get from the interleave schedule is going to be less. So it turns out that the pipelining schedule also affects throughput in a number of different ways. It turns out that you don't only have to use the interleave schedule, you could also use relaxed semantic schedules that affect the convergence rate of your model, but are much faster and kind of get rid of the pipeline bubble completely. But there are also other factors that affect throughput, like the global batch size. You remember from some of the graphs I showed you that throughput is influenced by the batch size, but the batch size also contributes to how fast your model converges. And there are also other hyperparameters like the micro batch size and so on. And so each of these different factors influence the amount of communication that we need to perform. It affects the size of the pipeline bubble. It also affects the memory footprint. And our paper has more details on how to think about these different factors. We also performed a bunch of different domain-specific optimizations on both the compute and the communication side in order to increase throughput. It turns out that when we are running things at large scale, even performance improvements like 10% are hugely useful. They greatly decrease the cost of training, and they also decrease your runtime in a very significant way. So one of the optimizations that we did on the communication side was exploiting the fact that there's redundancy in the communication patterns that we use when we combine tensor and pipeline model parallelism. And one of the key facts that we leverage with this optimization is that we have really fast interconnects within a server, but slower interconnects cross-server. So when we combine tensor and pipeline model parallelism, we end up sending the same tensor multiple times over InfiniBand. So here I'm assuming that my pipeline model parallel size is 2 and the tensor model parallel size is 2. And in this particular case, I'm sending the same tensor 2 times over the slower InfiniBand networks. And so what I can instead do is perform a scatter of the tensor at the send nodes, and then send these tensor chunks across the slower InfiniBand network, and then perform an all gather on the receive side. Turns out that the scatter and all gather are fast because they're performed within a multi-GPU node, and we can use NVLink. And we're essentially, in this particular case, reducing the number of bytes that we need to send over the InfiniBand network by a factor of 2. If we had if we are performing 8-way tensor parallelism, the amount of communication over the slower InfiniBand would actually decrease by a factor of 8. So we found that this optimization was hugely beneficial. So there's no quite trade-off here. We see that across a range of batch sizes, the scatter gather optimization improves throughput by about 10%. We also perform various domain-specific optimizations on the compute side. We found that using certain memory-bound kernels, either using PyTorch or doing it ourselves by writing custom CUDA kernels, really helped kind of keep operators compute bound as much as possible. And this gave us another throughput improvement, about 5 to 10%. So the end result is really efficient scaling. So this is a weak scaling experiment where we're increasing the problem size as we increase the number of GPUs. So as the number of GPUs increases, the model size also increases, and we're also increasing the batch size. So the rightmost point on this graph is a model with about 1 trillion parameters on about 3,000 GPUs, and we were able to train it at, I think, about 500 petaflops per second in aggregate. So all of these optimizations that I've talked about, really putting them all together gives us really strong scaling performance, even at quite extreme scales, which is great. So one thing I want to note here is, so this is my I'm bringing back my second slide, and one thing you might actually note here is that this graph kind of mysteriously ends at about November 2021, right? And so your natural question might be, why doesn't this graph actually have models from the last 2 years? There are actually a couple of reasons for this. The first is that we've actually seem to be now moving into a regime where companies are not so open about the details of the models they're training. For example, we only have rumors really about what OpenAI's latest GPT-4 model is. But more crucially, it turns out that model size is not the only dimension of scale that matters. So there was this really great paper from DeepMind last year that talked about this notion of compute optimal language models. And its main thesis was that we're actually undertraining large models. So what people used to do before was keep increasing model scale, but use the same number of same amount of training data, right? So people tended to use this magic number of 300 billion tokens. And what this paper basically showed was that this actually leads to suboptimal models. And instead, we need to be training these larger models for more tokens. And so actually, if I showed models from the last 2 years in the graph from before, I won't actually see this nice linear trend of model size increasing. It turns out that there are a couple of crucial systems implications that come out of compute optimal models. Because we are training for so many tokens, it's very common practice now to train models for trillions of tokens. It's becoming more crucial to use more GPUs to get results faster, as opposed to using more GPUs just to fit model parameters in GPU memory. And so really it's becoming crucial that we train models efficiently in regimes where the batch size per GPU is much smaller. For example, where batch size divided by number of GPUs is 1/4 as opposed to just 1, which is what I use in the experiments from before. It turns out that when the batch size per GPU is small, we actually get lower throughput. There are a couple of reasons for this. The first is that when the batch size is small, the number of microbatches in a pipeline is also small, which makes the pipeline bubble larger. Remember that the pipeline bubble size is P-1 divided by M. One way of mitigating this is to use the interleave schedule, but this trades off making the pipeline bubble smaller by also increasing the amount of communication. The other byproduct of making batch size per GPU smaller is we need to perform data parallelism communication more frequently. So let me illustrate this with a figure. So here I'm going to assume that I have 2 GPUs to begin with. I'm going to use a global batch size of 4. And I'm going to split this equally over the 2 GPUs I have. So each GPU is going to process a batch of size 2. And then it's going to perform some communication, right? So it's going to perform this already used communication to make sure that the parameters on both of these workers are the same, and then it can run another iteration, right? So now if I want to scale up, and reduce the batch size per GPU, what ends up happening is I need to perform data parallel communication more frequently, right? And so the upshot of this is that when I reduce my batch size, I'm increasing my point-to-point communication for pipeline parallelism. I'm also increasing my data parallelism communication. And so a crucial question in this new regime of compute optimal models is trying to figure out how to hide communication. That is, we want to overlap communication with the computation that we are performing. There are a couple of different things that we can do here. The first is we can observe that different microbatches are independent, right? The computation for these microbatches is independent. And so we can actually overlap the point-to-point communication in pipeline parallelism with the computation for the next microbatch. And we can also leverage the fact that computations in different layers or operators of the model are also independent. And so we can overlap all reduces needed for data parallelism with backprop compute for a different operator. So instead of waiting for the entire backprop to complete before we trigger an all reduce for the entire model, we can instead trigger smaller all reduces for different subsets of the model parameters. And that way we get overlap between communication and computation. So I want to wrap up my talk with some open questions that I think are going to be interesting to look at in the next couple of years. The first is, can we actually come up with techniques that reduce the number of bytes that we need to communicate over the network? So one way of potentially doing this is to quantize things like gradients that we communicate across devices. Right now, it's common practice, even if you're training a model using 16-bit precision, to all reduce gradients in 32 bits. So one natural question is, can we actually perform the all reduce in 16-bit precision as opposed to 32 bits? I also focus this talk largely on dense transformer models, but it turns out that people are using variants. So for example, a popular variant is mixture of experts, where we actually try to dynamically route input tokens to specific subparts of the model. In typical formulations, these mixture of expert models have many more weights than our traditional dense transformer models. And so it's an interesting question to figure out how to parallelize these models that have very different communication patterns compared to what we've been running for the last 3-4 years. And also, I think I talked a lot today about developing good human intuition about how to compose these different parallelism dimensions. But it would be really nice if we could kind of automate all of this away. And there are some recent papers that have attempted to do this, like Alpha. So just to conclude, I talked today about how carefully composing pipeline tensor and data parallelism is really important to training transformer models efficiently at scale. Our implementation is open source on GitHub. So if you're interested in training models efficiently, I encourage you to check that out, and I'm happy to take questions.
Awesome. Thank you so much. That was super interesting. And we loved all of the intuition that you were able to provide around the trade-offs of the different approaches with small scale examples. We have a bunch of questions from the students and from ourselves. So just kind of clustering these together a little bit. The first sort of category was around what the process to actually reason about these trade-offs look like when you're putting together when you're trying to start training for a new model. And you touched on this a little bit at the end about, maybe there are some recent methods that look at automating some of the pipeline decision approaches. So for these kinds of automated approaches, what are the state-of-the-art methods? What are the types of input features that they use and the types of speedups they provide? And touch a little more on that.
Yeah, these are great questions. I think when we
Also, end your screen share.
Yeah.
Thanks, man.
Yeah. I think when we're kind of trying to hand design strategies, we try to holistically think about these different factors that affect throughput, like the amount of communication, the pipeline barrel size, the memory footprint, and so on. And so you can essentially write out like expressions, for example, for the amount you need to communicate and how long you spend idle and so on. And so you can come up with pretty good heuristics for what you should actually set these values to. And then you can go and validate that intuition using experiments, right? So you can, we have a cluster here at NVIDIA that you can easily run experiments on, and then you can try to see if the throughputs in practice actually match your intuition. It turns out that a lot of these systems that are trying to automate this process are doing something similar. So they have expressions for things like amount of communication that you need to perform, and then the naive way of doing this is to do an exhaustive search over all possible configurations. That can become pretty expensive for really large models, and so a lot of the insight in these new works is figuring out how do you actually prune the search space so that you can do the search in some limited time budget, right?
I really like the discussion at the end about kind of this new regime of smaller models trained on larger token or more tokens that we're kind of getting into. I'm curious what you think. What happens when you kind of want to scale beyond that batch size equals 1 regime? So for example, if you're training, for example, 7 billion parameter model across 10 trillion tokens, you don't want it to take forever. There's only so many ways you can split it up in tensor and layer, and those sizes, you can't make the batch size too big either. What do you kind of see as the techniques that you can use in that sense?
I mean, I think you're right that you eventually get to a regime where you can't throw more compute at the problem. I think basically we can get to a point where the batch size divided by number of GPUs is 1/8. And even there, like you need to you need to make sure that your implementation is optimized so that you get good performance in that regime. Beyond that, I think we're right now we are kind of hosed. I mean, I think fundamentally that the problem eventually becomes that we need to do essentially distributed matrix multiplications over slower cross node links, right? And so we're not at the point yet, like these cross node links are not fast enough for that to be practical. And so right now we're kind of limited by the hardware, right? And so I think the best we can hope to do is batch size divided by number of GPUs is 1/8, because 8 is typically the number of GPUs that we have within a single node. But yeah, I mean, I think that's the best we can hope for right now. But hopefully, like interconnects continue to get faster. Yeah. And I think like one thing that's potentially interesting here is we are seeing newer architectures where we have another hierarchy of interconnects where, for example, like 256 GPUs have like fairly fast interconnects, and then you kind of go cross box after that. And so that could be an interesting data point to look at, right? Because then basically maybe we can start doing distributed MathML ops like across 256 nodes. I mean, that's actually not going to like work super well for the 7 billion model that you talked about, because each GPU then is going to like do like a really, really like narrow MathML, which is not going to be good for the performance that you see on each GPU. But that's perhaps the way forward. Yeah.
That's really interesting, especially as you're saying. I think like the H's or the amount of flops that they have went way faster than like the memory bandwidth, and I think it's going
exactly. Yeah.
Trade-off space that we're entering. You want to ask the
yeah. So one other set of questions was around what kind of work is being done on the networking side and the algorithmic side to improve training. So with things like traffic engineering and replay, or like bursty workloads, or the fact that during training certain GPUs can underperform or go down, and so things around fault tolerance. And so I know you mentioned largely on the networking side, just like faster interconnects would be the biggest direction for improvement, but more on the algorithmic side, what kinds of things are people thinking about?
Yeah, those are good questions. I think one thing is, I think people are trying to figure out how to reduce like the precision with which we perform communication. I think that's a pretty active point of work. I think another a thread of work here is trying to figure out how to offload things like all reductions completely to the NICs. So there's stuff like Sharp that removes the need for having to do like the summation in the all reduce, like on the GPU. Yeah, so you also mentioned things like fault tolerance and straggler nodes. I think that the stragglers are definitely a concern. We do go at the speed of the slowest GPU in this synchronous regime. You could try to make the computation asynchronous, but that has ramifications on things like convergence rate of the model, and because training these LLMs is so computationally expensive, people are actually quite risk averse in the types of things they want to try, because you might waste millions of dollars if you tried something and it doesn't pan out. So people are pretty conservative, and usually use tried and tested techniques. But you're absolutely right. Like in regimes where hardware is flaky and you have a lot of like slow GPUs, those slow GPUs are going to slow down the entire pipeline. And I don't think there's any good way of mitigating that without moving to a more asynchronous style of computation.
Awesome. Yeah, that's super interesting to hear about sort of the risk aversion, since I guess in the history of our lab, at least, there's been a lot of work thinking about like synchronous versus asynchronous computation here. So interesting to hear about.
Yeah.
Well, one last question to wrap up. So Fyodor, an ex-host of MLSys seminar, has asked on YouTube Live. You've been here twice now, so you talked about GPU cluster scheduling, earlier you're talking about your work at NVIDIA and training large models. So any speculation on what you'll be talking about next time you're on the MLSys seminar?
Yeah, I think a lot of what I've talked so far has been on the training side. So I think like hopefully next time I come on, I talk more on the inference side of things. I think inference is super interesting. It's not a computationally bound workload, at least the way we do autoregressive inference. And so the throughput we see on modern accelerators is quite a bit off of peak device throughput. And so I think there's a lot of systems innovation to be done here to improve the throughput we see with autoregressive inference, and that's something I'm excited about going forward.
Awesome. Well, thank you so much, Deepak. This was an amazing talk and discussion. Thanks everyone in the audience for coming in, watching and joining us and asking questions. Just want to mention that we'll be updating the schedule for the rest of the quarter on mlsys.stanford.edu, and subscribe to the mailing list, subscribe to the channel, and see you all next week. All right.
Bye,
Thank you.
Yep. Thanks for having me.